Now in this video, we're going to look at the movement of particles from one region to another. And the name given to the movement of particles is known as diffusion. Alright, diffusion occurs, or the movement of particles occurs from a region of higher concentration. That means you have more of that particle to a region of lower concentration. Alright, so it will move from a region where you have more of that particles to a region where you have less of it. A typical example of diffusion would be that of perfumes. So for example, when we smell the scent of a perfume, what is happening is that the particles in the perfume actually diffuses into our nose. That's how we smell the scent of a perfume. So the particles will move from a region of higher concentration to a region of lower concentration. And when will the movement or the net movement of the particles stop is when we have an equal concentration of that particle, of that type of particle everywhere. Okay, so the key concept to note here is that if we leave diffusion to occur for a long period of time, what we will get is a sample of uniform distribution. So let's take a look at this question here. This question, we have two different gases, nitrogen dioxide in a gas jar on top, and we have air contained in a gas jar at the bottom. Now at the start, the two gas jars are separated by a glass plate, so the two gases cannot mix. But what happens is that the glass plate is removed, and then the question is asking what would be the observation in both jars after a long period of time. Okay, so why would there be any observation in the first place is because nitrogen dioxide is a brown gas. Okay, air is essentially colorless. So what happens if we remove the glass plate is that nitrogen dioxide can now diffuse downwards and air can diffuse upwards. So what happens, what would we observe if diffusion occurs for a long period of time? The concept to recall here is that if we allow diffusion to occur for a long period of time, we will always end up with a uniform mixture. A uniform mixture meaning we have equal amount of nitrogen dioxide everywhere, we have equal amounts of air everywhere. So the observation that we should make is A. So the next important thing that we need to learn about diffusion is this, that the rate, how fast the particles move or how fast the particles diffuse, depends on two factors. One is temperature, two is the mass of the gas particle. Okay, so what happens is that when temperature increases, you can imagine when temperature increases, the particles will have more energy. Alright, and when the particles have more energy, they can move faster, so the rate of diffusion would increase. Okay, how about mass? Now, in a situation when an elephant and a leopard is given the same amount of energy, alright, meaning they are given the same amount of energy, which animal will move faster? Alright, I hope that you can imagine that and know that the leopard will move faster. Why? Because the leopard has a lower mass, so when they have the same amount of energy, the one with the lower mass will end up moving faster. So it's the same with gas particle. When the mass of a gas particle increases, the rate of diffusion will decrease. So the natural question now is, how do we know the mass, or how do we calculate the mass of a gas? We have briefly looked at it in the first chapter when we were deciding whether a gas is denser or less dense than air. Alright, so we're going to revisit that again. To obtain the mass of a gas, we need to refer to the periodic table. As mentioned, for every element in the periodic table, there are two numbers associated with it. and the larger of the two number represents the mass of an atom of that element. For example, if we look at carbon, carbon has two numbers, the larger of which is 12. What does that tell you? It tells you that the relative mass of an atom of carbon is 12. So let us now try to apply what we have learned in a very typical example of diffusion. So in this example, we have a very long glass tube, and at one end of the glass tube, we have cotton wool soaked in concentrated ammonia solution. On the other end, we have another cotton wool that's soaked in concentrated hydrochloric acid. Now what is going to happen is this. The cotton wool containing the concentrated ammonia solution, some of the ammonia is going to evaporate to form ammonia gas. At the end, where you have a cotton wool soaked in concentrated hydrochloric acid, some of the acid is going to evaporate to produce hydrogen chloride gas. Okay, what happens next is that your ammonia gas will diffuse to the right, your hydrogen chloride gas will diffuse to the left. Now, the magic happens when the two gases meet. So, when the two gases meet, they actually undergo a reaction and they form ammonium chloride. So, ammonium chloride is actually a white solid. Okay, so if you perform this experiment in real life, you'll find that there is a ring of a white solid that appears somewhere along the glass tube. So the question now is, where will it appear? Is it in the middle? Would the white ring fall somewhere in the middle? Or would it be closer to ammonia? Or would it be closer to hydrochloric acid? So to answer that, let us analyze the two gases that are diffusing. One gas is ammonia. The other gas is HCl, or hydrogen chloride. So to know where they will meet, we need to think about their relative rates of diffusion, which therefore would depend on the mass of the two gases. Alright, so let's try to compute the mass of ammonia. If you refer to the periodic table, nitrogen has a mass of 14, hydrogen has a mass of 1. And since there are 3 hydrogen atoms in ammonia, the total mass of ammonia is 17. Next, we look at the mass of hydrogen chloride. Hydrogen chloride, for hydrogen, it has a mass of 1 again. Chlorine has a mass of 35.5. So hydrogen chloride would have a mass of 36.5. Now, if we compare the masses of both gas particles, you will realize that hydrogen chloride has a larger mass. Larger mass meaning it will diffuse, the rate of diffusion will be slower. Alright, so what happens is that ammonia, having diffused faster, will cover a larger distance compared to hydrogen chloride in the same period of time. So the white solid will form nearer to your cotton wool that's soaked in hydrochloric acid. So again, if you were to perform this experiment in real life, that is what you will see. You will see a white ring that's formed closer to the cotton wool soaked in hydrochloric acid. Now let's try again whatever we have learned in another example. So here we have 4 balloons. Each balloon is filled with a different gas, and the gas will diffuse out of the balloon. So now we are supposed to figure out which balloon will go down the quickest, meaning the gas will diffuse out of the balloon the fastest. And once again, in order to know which gas will diffuse out the fastest, we need to analyze the mass. In the interest of time, I'm going to give you the masses of the 4 different gas particles straight away. If you want, you can pause and try it yourself first before resuming. So the mass of carbon dioxide is 44, the mass of methane is 16, the mass of nitrogen 28, and the mass of oxygen 32. Okay, so if we compare the masses, we find that methane has the smallest mass amongst the four. What does it mean? It means that it's going to diffuse the fastest, so the balloon B will go down the quickest. Now let's take a look at another typical diffusion question in the O-levels. Now this kind of question is so famous that we name it the porous pot question. So what is happening over here is that we have a porous pot over here in the diagram. And what does a porous pot mean? Porous pot means that the pot has holes in it, very tiny holes, such that gas particles can diffuse in and out of the pot easily. Okay, so if we were to look at the diagram, there is a gas inside the porous pot, there is a gas outside the porous pot. Okay, so what it means is that the gas Q inside the pot can diffuse out of the pot, whereas gas P can diffuse into the pot. Now, depending on the gas particles in P and Q, we will see two different scenarios. In scenario 1, gas P diffuses in faster than gas Q diffusing out. In scenario 2, gas P diffuses in slower than gas Q diffusing out. Okay, so these are the two possible scenarios. Now let's observe what happens to the water level in each scenario. So in scenario 1, where gas P diffuses in faster than gas Q diffusing out, to know what happens, the trick is to ask yourself, after some time, do I have more or less gas inside the porous pot? I repeat again, to know what happens to the water level, the trick is to ask yourself this question. After some time, will I have more or less gas inside the pot? So for scenario 1, where the gas P diffuses in faster than gas Q diffusing out, after some time, we will have more gas inside the pot. And if we have more gas inside the pot, the pressure inside the pot would increase. So it will push the water level on the left down, and the water level on the right would go up. Okay, in scenario 2, where gas Q diffuses out faster than gas P diffusing in, after some time, we will have less gas in gas Q inside the pot. So when we have less gas inside the pot, what will happen is that the pressure inside the pot would decrease, causing X to rise, whereas at the right side, the water level will drop. Okay, so I hope that you can see the difference between these two scenarios. Now the next question to ask is, when would we get scenario 1 and when do we get scenario 2? For scenario 1, gas P diffuses faster than Q. Alright, so in what situation would P diffuse faster than Q? Is when the mass of P is less than the mass of Q. So the opposite applies to scenario 2. For scenario 2 to happen, it means that gas Q diffuses faster than P. So when would that happen? Is when mass of Q is less than the mass of P. So with that in mind, let us go back to the same question and try to apply to see what happens to the water level. So for this question, we want the water level at X to rise. Okay, for X to rise, meaning if we look back at the scenario, it means we are looking at scenario 2, where after some time we have lesser gas inside the pot. So for that to happen, Q must diffuse out faster than P diffusing in. And for that to happen, the mass of Q must be less than the mass of P. So right now, let's analyze the masses of the different options and see which one satisfy this criteria. The mass of carbon monoxide, 12 plus 16, so that will be 28. Fluorine is 19, so fluorine gas would be 38. Once again, neon is 20. Okay, I've written down the masses of the different gases in the options. Now let's look at which one satisfy the condition that was mentioned, where mass of Q is lesser than mass of P. So there's only one option that satisfies that, so that is option B. Now let's look at one last question. Again, this is a porous pot question. So now we have oxygen inside the pot, we have another gas that's outside. So the question now is asking which gas will cause the water level at Y to rise. Okay, so if you analyze the scenario now, for the water level at Y to rise, it means that the water level on the left would have to drop, meaning the pressure inside the pot must increase after some time. For the pressure to increase, it means that the number of gas particles inside the pot must increase after some time. And for that to happen, it means that the gas inside must diffuse in faster than the gas inside diffusing out. So for that to happen, it means that the mass of the gas outside must be smaller than the mass of oxygen. Now there's actually a trick, a little trick in this question, which is in finding the mass of oxygen. So very often students will tell me that the mass of oxygen is 16 because that is what is shown in the periodic table. However, for this type of question, we must be aware of something called diatomic molecules. Okay, there are certain elements, there are certain non-metallic elements that exist naturally by combining with itself. Okay, so like for example, oxygen is not stable on its own. So in nature, oxygen is found combined with itself. So there are two atoms of oxygen in oxygen gas. Alright, so the elements that exist as diatomic molecules, these are the ones that you have to remember. And there's one way to help you remember that is have no fear of ice cold beer. Okay, so these are the elements that when they exist in nature, they exist as diatomic molecules. That means H2, N2F2O2, I2, Cl2 and Br2. Alright, so when we compute the mass of these diatomic gases or these diatomic molecules, we have to bear in mind that there are two atoms of the element in each molecule. So the mass of hydrogen is not 1 but 2. The mass of nitrogen is not 14 but 28. And then mass of fluorine is 38 and not 19, and so on. Okay, so the mass of oxygen is not 16 but 32. So right now we are supposed to look for a gas which has a mass that's lesser than 32. So let us again compute the masses of the four gases. We have 44, 71, 16, and then what is this? 32, 40, 46. So by comparing the masses that of all the four options, we can see that methane, option C, the gas is small, has a mass that's smaller than oxygen. Therefore, if we have methane in the gas as the gas in the beaker outside the pot, it will diffuse in faster than oxygen diffusing out. After some time, there will be more gas inside the pot. The pressure will increase, therefore the water level on the left will drop and the water level at the right would rise.